further elaboration. And today, so just to remind that ENSUS discussions are an action of the ENSUS chair, and it's an action that has seen quite a good success in the first, second, and third editions. I'm sure this edition as well. So let me present Professor Chris Hardacre. Professor Chris Hardacre is head of the School of Natural Sciences at the University of Manchester. He obtained a PhD from Cambridge University in 1994 and moved to Queen's University in Belfast in 1995. And he was appointed as Professor of Physical Chemistry in 2003. In 2016, he moved to the University of Manchester. He was awarded the Royal Society of Chemistry Encouraging Innovation Award with Merck Chemicals Ltd, and was part of the team to win the Queen's Anniversary Prize for Further and Higher Education. In 2013, he was the inaugural winner of the IChem's Andrew Medal for Catalysis. And in 2022, he won the Tilden Prize from the RSC. His group has strong research interests in catalysis and ionic liquids. So many subjects that could interest, I'm sure, many of our researchers, and we are very honored and happy to have you with us, Professor. Floor is yours.
Thank you very much indeed. And thank you very much for the invitation. It's a great pleasure to be here. I've been speaking to Joanne about Morocco, I think now for 3 years or something like that. So, I've known Joanne for a large number of years. So it's great to see him here and to be able to interact with you. So thank you very much for the invite. I was hearing actually Morocco is the birthplace of a university. So apparently Fez, was that right? Was I speaking? Fez in 800 and something was the birthplace. So we're a bit younger than Fez, 1824 for the University of Manchester. But some of the I just thought I'd tell you a little bit about the University of Manchester and Manchester as a place. So it's sort of, I think Birmingham sort of Birmingham and Manchester sort of vibe of being whether or not which is the second city past London in the UK, but we're going to say we are. But I think more importantly, it's classed as the place where the Industrial Revolution started in the world, and people like Reynolds were there. The first big computer was there as well. Rutherford split the atom in Manchester. We've had a number of Nobel Prize winners, but I think for me this business about the Industrial Revolution was interesting because it was the birthplace of engineering, actually. So the first lectures in mechanical engineering or civil engineering or electrical engineering or chemical engineering were held in Manchester. In fact, the father figure of chemical engineering, George Davies, gave the first lectures. And he was actually a chemist. He wasn't a chemical engineer, but he was quite a visionary. He used to say things like that the importance of chemical engineering was to allow our waterways to not be polluted, our ground to not be polluted, and our air not to be polluted. And this was in the 1800s. It's taken us a long time to actually realise that actually what he was saying was important, but he was quite impressive with that. Give you some idea about the university itself, some statistics. So we have around about 40,000 students. There's about a quarter of those students are international students. In the faculty, we have somewhere of the order of just over 1,100 academic members of staff in the Faculty of Science and Engineering. So you can see it's a relatively large university for the UK. In fact, it's the largest non-campus-based university in the UK, and it's sort of ranking about 28 in the world. So what I was really going to talk about today was something I know that's close to everyone's heart here in the university and in Morocco, which is about energy, and in particular, what we need to do to be able to do things more sustainably. And I think this outlook that BP gave, where they show what their outlook is for energy by in 2030 is quite stark. On the left-hand side here, the left-hand side here, you see the amount of energy that BP think we're going to be needing in billion barrels, billion tons of oil equivalent up to 2030. And you can see it's basically doubled since 1990. So we're still increasing in our energy usage. But the share of the fuel that we're going to use from 1990 to 2030, you can see renewables has increased dramatically, nuclear's gone up a bit, hydroelectric's gone up a bit, things like coal has remained static, natural gas has gone up a bit, but oil's gone down. And you might think, well, hang on a minute, that's all great. That means we're going to be sustainable. But the trouble is that 16.6 billion tons of oil equivalent multiplied by 27.2% is still higher than the 8.1 that we had in 1990. So we're still, even in 2030, going to be using about 80% of our energy pool will be from hydrocarbons. This is not a sustainable future. So what can we do about it? Well, we already know what the impact is likely to be of using these fossil fuels. Of course, I don't need to go through these graphs, but they're pretty stark in terms of the amount of CO2 that we'll have in the atmosphere and the potential change to our temperatures and the global warming potential for CO2. And there's this magic 2 degrees centigrade figure beyond which we don't want to go because of positive feedback loops and so on and so forth, and massive changes to our environments and so on. And so we need to maintain and limit our CO2 to sort of this level to be able to keep the temperature increase to below this 2 degrees. And we can do this in a number of ways. And you can see here a pie chart of where that CO2 is coming from. A lot of it is man-made. Some of it comes from agriculture, but a lot of it is man-made. And most of it comes from non-residential things. So most of it is transportation, electricity production, or industry. So how are we going to do something about this? Well, we need a different source of that energy, of course. And you have a really good one. I didn't see much of it yesterday, but I've seen quite a lot of it today. So we see the nice sunshine today. It was nice pouring down with rain. I was welcomed by rain, which I left in Manchester. So one source of that energy is the sun. And you have that natural resource, of course, in Morocco, which is more than we have in the UK. What we have in the UK, of course, is lots and lots of wind. So we have a lot of wind farms and so on. And in fact, actually, we have had in the UK some days where there has been no use or virtually no use of fossil fuels to generate our electricity, which is quite remarkable. So we have got to a point where quite a lot of our electricity is being generated via renewable sources. And of course, some of the problems with these sources is that they're not very transportable. They're not very good at being stored, unlike oil. Okay, oil we have in a tanker, we transport it, we use it, and it's all great. That's fine. But electricity we need to store. And I heard today about your lithium battery work, for example. And this is one way of storing our energy and then using it when we want to on demand. Because quite often, for example, where the wind is not where the population is. So if I think about the UK, it's very windy in the north of Scotland, but there's not a lot of people there. It's not so windy in London, but there's an awful lot of people there. So how do you get that energy from where it's being generated to where it's being used? And batteries are one of those opportunities. But we need to create things like biofuels, things that we can make out of biomass and so on. And we need to use things like hydrogen. Hydrogen has its problems, and hydrogen storage being one of those, but we can convert that hydrogen into other things that we can store and can use, and that's where the conversion of biomass and carbon dioxide comes in. And you'll see throughout the talk that actually hydrogen is there all the time. Now, we need a reductant. You need to be able to create hydrogen. So how do we do that? And you in Morocco have an opportunity to contribute to this because of your biodiversity and your sunlight and the sea that you have around you and so on. So we need to go from this type of thing, the oil refinery, to this type of thing over here, which is the biorefinery. How do we do that? Well, it won't surprise you to know that you need catalysts to do that. And so what we do is we use catalysts to try and understand how to develop new processes for sustainability. And that's what I'm going to talk about today. So I'm going to talk about 3 different types of things, and actually one of these, which is the biomass transformations, I wasn't going to talk about at all until I had the tour yesterday, in which case I changed my talk a little bit, and I'm going to talk about that today. So I'm going to talk about CO2 capture and utilisation using these things called ionic liquids, and I'd like to thank Joanne a lot, because actually Joanne has been a major part of that work. I'm going to talk a bit about plasma catalysis. There's a different way of activating molecules and reacting them on the surface of heterogeneous catalysts. And I'm going to talk a bit about biomass transformations using catalysts for both fuel production as well as hydrogen production. So, why do we want to do CO2 capture and storage? Well, of course, I've already explained. We want to try and limit the impact of that CO2 on the environment. We can do it a number of different ways. These are some of them. We can put it into deep saline aquifers and store it there. We can do enhanced oil recovery. Many of these are not used. They are available to us, but actually economically, it's not been shown that we can do this very straightforwardly. In fact, actually, this type of thing here, the enhanced oil recovery and the deep saline formation, there was a whole setup to be able to do this in Scotland with the North Sea oil rigs, but never has it actually been utilised today. So we have the infrastructure, we know how to do it, it's a good way to do it, but we don't quite do it at the moment. So there are an awful lot of ways to do this. We can store it in stable materials, but a lot of this keeps the CO2 as CO2. It either binds it very strongly. For example, if you take calcium oxide, combine it with CO2, you make calcium carbonate. You can't really do anything with that CO2. If we put it down in deep saline aquifers, then again, it's stored, but you're not really utilising that carbon. So what can you do with that carbon? Well, you want to be able to do something with it somewhat akin to the natural carbon cycle. Now, the natural carbon cycle is very straightforward. Okay, it takes atmospheric CO2, it does photosynthesis. You make fossil fuels, or you take it through plants and animals and so on, and then you use it, and then it goes through this cycle here. We can do an anthropogenic carbon cycle, though, and actually utilise that CO2. We can take the CO2, we can do carbon capture, we can store it, we can use hydrogen to do the reduction of it. We can then take it through to methanol or dimethyl ether or hydrocarbons of some other description, making synthetic fuels or pharmaceuticals and so on. You use it, you burn it, but then you put it back in the atmosphere and it just goes through this virtuous cycle. You're keeping the carbon in play. You're not increasing the carbon dioxide in the atmosphere, but you are able to use it for what we want to do. But of course, you need an energy source to be able to do that. CO2 is a thermodynamic sink. It's a hard molecule to do something with. So you need to be able to put energy in to be able to get it to react. And one of those energy sources, of course, is the sun. And the sun can be used to generate electricity that you can do something with, or you can do it directly. So these are all the types of ways that you can use CO2. And in fact, again, in the UK, what you find is that all of these industries are interlinked. So we have our energy prices go up. Then a fertilizer factory in the northeast of England decides it cannot afford to make fertilizers in the UK. It's going to make them elsewhere because the energy costs are too high. It then shuts down. The amount of CO2 that you then have then disappears, and suddenly you can't do medicine. You can't make carbonated drinks. You can't transport fuel or food around the place because you need dry ice and so on. So all of these industries are actually all interlinked. So we've got to be able to understand that whole process. But you can take some of that CO2 via direct air capture or via the capture of it from flue gases, for example, and you can make a whole range of compounds. So you can make secondary chemicals, methanol, urea, methane, CO, fertilizer, liquid fuels, and so on. And that's where we've been interested. So how is it conventionally captured? Well, it's conventionally captured via this type of process. So you take monoethanolamine in an aqueous form and you react it with CO2. It's a very good technology. It works very well. It is used already. It's got high reactivity, low cost, and good CO2 capacity. Brilliant. What's the problem with it, though? Problems are it's pretty volatile. So you actually lose amine. So even though it's low cost, you're losing amine. It's pretty intensive in terms of energy if you want to regenerate it. The amine group binds that CO2 very strongly, and therefore to get that CO2 off again, you need to put lots of energy in. Where does that energy come from? If you burn methane to get that energy, of course you generate CO2 again. So you've got to think about how you're going to do that. And also because of the hydrogen bonding nature of this and the way that it has water there and production of salts, it's pretty corrosive. So are there alternatives? Well, I know you know there are alternatives because you're doing research in the area, but we were really looking at ionic liquids as a possible replacement of this monoethanolamine and have studied it quite a lot. So what is an ionic liquid? An ionic liquid is exactly what it says on the tin. It is a liquid that is only made up of ions. And these are liquid at room temperature, or low temperature. And so instead of melting at 700, 800 Celsius like sodium chloride would do, you make the ions big and bulky, you make them so they don't pack together very well, you delocalize the charge, and suddenly you reduce the lattice energy down and you get something that is now melting at room temperature. So this is an example of an ionic liquid. It's not one that we've used for this reaction, but we have used it in the past. So the ionic liquids that we have chosen to use are these things called super base ionic liquids. And that's some of them that you can see here at the bottom. And basically the anion here, which is shown here and here and here and here and here, is a deprotonated amine. So we've removed a proton from the amine and we've created an anion. So can they be used for CO2 capture? Of course they can. In fact, they have been used they were discovered in about 2010 by a group in China that have done quite a bit of work in this space, and they find that they're very good for CO2 capture. What nobody was really looking at, though, is what the effect of everything else that you might have in that gas stream were on these systems. Of course, you don't have a pure CO2 and helium gas stream when you're doing it in industry. Of course, there's other things there. There's water there. There could be SO2 there. There could be NO2 or NO there, etc. And so we were interested in understanding what the effect of those impurities were. So does it work? Of course it does. These are the set of ionic liquids at the side here. And this is what happens under dry conditions. This is gravimetric uptake of moles of CO2 per mole of ionic liquid. And you can see you're getting up to about 1.2 moles of CO2 per mole of ionic liquid. It works pretty well. Water, the presence of water can have a positive and a negative effect on the CO2 uptake, but it still works pretty well. Oh, that's interesting. That's supposed to be around that one. Anyway, not to worry. The key thing is, can you regenerate the ionic liquid? Because ionic liquids are not cheap, but can you regenerate them? So you can do a temperature swing absorption, a desorption profile. So you absorb at room temperature, you take them up to about 80 Celsius, 75, 80 Celsius, and you can desorb the CO2 fairly straightforwardly. And it's totally reversible. This goes on and on and on, up to sort of 25, 30 cycles we've done, and it works perfectly well. That's great. And you can do this in the presence or in the absence of water. You can monitor the uptake of the CO2 using NMR spectroscopy. So you can see here the peak here for the carbon dioxide attached to the ionic liquid, and you can you can correlate that with the gravimetric analysis, and all fits together perfectly well. So that's very nice. What you also find, of course, if you analyze the data, one of the things that we're interested in is understanding the interactions between the molecules and the solvent and so on. So we use NMR to do that. And one of the things you can see here is if I look at the peak strands here, which are basically these CH2 groups next door to the phosphorus, you can see they shift depending on whether you've got the CO2 there or not, or whether it's wet or not, and so on. And you can see they shift. And so what you're seeing there is actually the interaction with the cation is also significant. In fact, in particular, the interaction with these CH2 groups right next door to the phosphorus, which are the most acidic of the hydrogens in the system. We've checked this with modelling work. So quite often in my group, we do experimental work, but we also check things with collaborations in modelling. And if you look at the modelling work, you can see that the anion, with or without the CO2, does interact with that CH2 group that we showed earlier on. There's the phosphorus in the middle, there's the CH2 group, and you can see the anion interacts with those acidic protons, and that still occurs when you have the presence of the CO2 there. These shifts that you get in the water versus the dry systems indicate that actually the CO2 does compete fairly well against water for the protonation of the amine, which is also very helpful. So as I said, water is one of the impurities, and water is actually fairly easy to look at because you can saturate the system with water. But what happens if you have perhaps a reversible gas within there? Using gravimetric analysis, it can be quite difficult to ascertain what is changing the mass. Is it the CO2 or is it the other impurity that you have in the gas feed? And so we've developed this system, which I know Joanne is getting a similar system here, where we use a mass spectrometer to look at breakthrough curves. So we have a liquid, we pass our gas through our liquid, and then we monitor what is coming out at the other end using a mass spectrometer. And you can see what happens here. What you basically get is you get a breakthrough curve, and then the area between the analyte that you're interested in against an inert material, when you switch it, gives you the amount of material that you're absorbing. And then, of course, you can desorb and measure the amount that you've desorbed and correlate the two together. And they should, if it's totally reversible, they should be the same. But of course, if it's partially irreversible, you'll get some left behind in the liquid. And so we've done this so because you can monitor the interactions for all of the gases using the mass spectrometer for looking at the interactions that we have between impurities. So here's some data that we have for CO2 and SO2. You can see here in blue, this is without SO2, this is with the SO2 there, but this is the CO2 going up. You look at the area under here, that gives you the amount of CO2 that you've got there, and you can see the desorption peak of CO2 afterwards. The orange line is the amount of SO2 that you're getting there. And what you notice is you don't get any breakthrough of SO2. In fact, the SO2 all remains within the ionic liquid. It doesn't desorb. By the time you've got to cycle 8, you start to get some SO2 breaking through. It's showing you that the SO2 is much more strongly bound than the CO2 is, which you probably would expect. But what you also see, of course, is that as you do cycles of CO2, SO2, the SO2 just carries on going up, but the CO2 uptake gradually comes down. It becomes less and less likely that you can use this ionic liquid to capture CO2 in the presence of SO2. We can look at the infrared spectroscopy, and the infrared spectroscopy tells us what is happening, and basically it's not surprising, but the SO2 binds to the anion, as you can see here, and displaces the CO2. So it stops subsequent binding of the CO2. Interestingly, when you look at other molecules, this isn't the case. If we look at the amount, of NO that we can get in there, or NO2 that we can get in there, you can see that we can get some irreversible binding or relatively good uptake of NO, but it's very difficult to take up NO2. And you can see what happens. This is if you have the CO2 uptake in the presence of NO versus NO2 versus SO2, you can see the NO does not affect the CO2 binding. The presence of NO2 and SO2, however, do. So even though you've got a very good absorbent for CO2, in a real system, you need to design your system so that the effect of the impurities is small. So that system was this benzimidazole ionic liquid. If I change the anion, I get a different effect. This is the 1,2,4-triazolide-based ionic liquid. The presence of SO2 only changes the amount of CO2 binding very slightly. So actually, it's not a big effect. So you can use this to design a new system. I'm going to skip over this just a minute. So you can use the fact you can tune the anion to help you. So if I look across here, so this is the benzimidazole system, and this is the same cation, but with the tetroxylide system. The CO2 uptake with the benzimidazole system is very good. The CO2 uptake for the tetroxylide system is terrible. So you would never use this system for CO2 capture. SO2, though, binds very well to both of them. Okay, so that's good. But that means that if you design a system such that you pass your CO2 and SO2 system through this system first, and then this system, you can take out the SO2, and then you can absorb the CO2. So that's what we did. We designed the system. Here's the tetroxylide system. Here's the benzimidazole system, and it works perfectly well. You can see here, this is without that tetroxylide system. The benzimidazole just dies, as we saw before. You get a small decrease in the CO2 system because you get a bit of transfer of the SO2 through the tetroxylide system. It's not perfect, but you can see that actually it doesn't die and it evens out. So we can get an effective system to be able to do CO2 capture in the presence of other impurities. And this is it in Aspen. You can see here, we get the feed coming in here. Here's our flue gas feed. We get our TETS-based ionic liquids first here. You then do a separator so that you remove the TETS, you release the SO2 because you can then use it to make sulfuric acid. You recycle the TETS. You then have the rest of the CO2 through here. You then pass it through the benzimidazole system. You release the CO2. And now you've got a clean amount of CO2 and you've got a clean amount of SO2 in your whole system. And it's actually relatively low energy because you're only heating this up to about 70 degrees. You've got very good recyclability of your ionic liquids, and it seems to work pretty well. Importantly, this learning that you can do from these ionic liquid-based systems, you can then apply to different other systems. So this is some work that we've worked with Infinium on. And Infinium are a large lubrication manufacturer. And one of the problems with lubrication oils is when in the internal combustion engine, you produce NO and NO2 in your exhaust. And that NO and NO2 will react with the lubrication oils and they'll oxidize them. Their oxidation makes the viscosity go up, which means that your energy or your fuel economy goes down in your car. You have to change your oil more regularly and so on. So what they've been trying to do is work out additives that they can put into the oil to stop it from oxidizing and nitrating. And so we looked at some ionic liquids because we know that they can capture the NO, and you can see here a hexanoate-based ionic liquid which captures the NO perfectly well. And you can see here, this is the nitration of an oil. So this is what the nitration looks like without the ionic liquid. And this is what the nitration looks like with the ionic liquid. You have an 80-odd% decrease in the nitration because the ionic liquid captures the NO. And so this is being looked at as a possible way of reducing down the oxidation and decomposition of the oils. Okay, I've talked a lot about capture. I haven't talked about utilisation at all. Of course, what we'd like to be able to do is do things like CO2 reduction. The issue for us with CO2 reduction, of course, is that it's a very stable molecule. You want to make it into the bent form. Ionic liquids have been shown to be able to reduce down the overpotential, but they've been mainly focused on ionic liquids that physically absorb CO2, whereas actually what we're interested in here is an ionic liquid that chemically absorbs CO2, and you can see when you chemically absorb it, you make it into that bent form. So can you then do something with it? Of course, the answer is yes, and you can see here cyclic voltammetram. I'm not going to go through it in any great detail. I can go through it if you like, but this peak here is when you have ionic liquid and you have CO2 and you have water present. And you can see that is there when you have all three present, whereas it's not there when you don't have those three present. And this peak here on the reduction side is the reduction of that CO2. And in fact, you get a very low overpotential because the ionic liquid activates your CO2 electrochemically, and therefore you can reduce it at low potentials. In fact, you need them both. You need the water and the CO2 there because you need to have a reductant there as well. And this gives you some electrolysis information. What are you forming? Well, actually, you're forming mainly formate. It's only when you get to much lower reduction potentials that you then see some CO and you see some hydrogen being formed, but you see lots of formate. It's got a very good Faradaic efficiency of about 95%, and it has an applied overpotential of 0.17 volts. This is compared with an applied overpotential of 1.5 volts that you'd conventionally need to be able to reduce CO2 down. And so it gives you a real opportunity by using the ionic liquid effectively as a catalyst to be able to reduce down the energy that you need to put in. You can, of course, do it in mixed feeds, and this also gives you some idea. This is with the presence of SO2. You can see here, again, you have a low potential, and you can still get formate even in the presence of the SO2. So it does give you an ability to do that in the presence of impurities. So we have an outlook like this, where we can use the CO2 to capture a reductant, in this particular case, hydrogen from water, make formate, and then release that hydrogen. And so you can store hydrogen in the form of a chemical storage element. Okay, I'm going to switch tack and quickly go on to plasmas. So what are plasmas? Plasmas are the fourth state of matter. We've been looking at plasmas, in particular non-thermal plasmas, where we're activating the electrons rather than the nuclei. And we're looking at these so that we can activate molecules in the gas phase easily without having to heat everything up. And then we can try and capture those excited molecules using a heterogeneous catalyst, so a solid-based catalyst. And you can see here at the bottom, it's a very straightforward way of doing catalysis. You have an electrode down the center of your catalyst bed, you have an electrode on the outside of your glass tube, and you effectively put a discharge across it. And you can see that happening here in purple. And what we're trying to do is we activate the molecules in the gas phase, and we capture those short-lived molecules, those radicals, those ions, whatever they might be, and we react them on the surface of our heterogeneous catalyst. We've done a huge amount of work in this space. We've looked at CO2 hydrogenation, methane oxidation, reforming processes and water gas shift. I'll talk a little bit about this one and this one. What we're interested in is how the plasma changes the catalyst structure, how the plasma changes the surface oxidation state, but mostly we're in, which is what I'll go through. When you're talking about hydrogen production, this is the normal way that you make hydrogen. You take methane and you take steam, you do steam reforming, you produce a mixture of hydrogen, CO, CO2, water. You do a high temperature water gas shift reaction, which is the reaction between CO and water to make CO2 and hydrogen. You then do a hydrogen purification step, and then you make it, then you put it through a fuel cell. And of course, the hydrocarbon at the front end here, you can use methane, which is conventionally used, or you could use biomass, which would also be interesting. This is the step that we're most interested in. We're interested in the hydrogen purification step because you require low temperature water gas shift. And this is what happens thermally. So what we do is we monitor the CO conversion. So we take CO and react it with water. We monitor the CO conversion against temperature with a given set of catalysts. The lower the temperature of the light-off, the more active the catalyst is. And this black line that you can see above here is the equilibrium conversion. And this is your problem. As you go to higher temperature, the equilibrium conversion goes down. But as you go to higher temperature, the activity of your catalyst goes up. So your rate of the reaction goes up, but you're then limited by thermodynamics. So what you need to do is make a catalyst that operates at as low a temperature as you possibly can. So you're not then limited by equilibrium, but you still want a really active catalyst. And we weren't able to find one. That's the point, really. That's why we chose plasmas. These are a set of catalysts that we have developed. You can see some terrible ones, like this gold on titania one. The platinum on ceria one is not too bad. It's active at about 250 Celsius. This gold on ceria zirconia catalyst down here is active at 100 Celsius, but only gives us 20% conversion. So its kinetics aren't quick enough to give us our equilibrium conversion at the temperatures that we'd like it to be. So can you use a plasma to be able to activate the molecules and get a lower temperature activity? So we have our standard setup. I can go through this in more detail later, which is a fixed bed reactor. We take our gold on ceria zirconia catalyst, which is our best catalyst that we've got there, and we take a number of feed conditions, but they're essentially the water gas shift feed conditions. I wouldn't be telling you this story if it didn't work, of course. So here is the catalyst. So this is without a catalyst present. This is the low temperature commercial catalyst. So this is using a non-thermal plasma, and it gives you reasonable activity at about 100 Celsius. The temperature of the plasma is around about 100 Celsius. But the gold on ceria zirconia catalyst is giving you very good activity. The thermal case was giving you 20%. We're now up to 70% conversion. So we've been able to activate our gas phase and now get really good conversions at low temperature. What about the activation barrier? What is happening when you're doing this? Well, one of the things that the plasma does is it enables you to lower the activation barrier. Under the thermal conditions, the activation barrier is about 40 kilojoules per mole. Under the plasma conditions, it's 7. So that's why you've now got really good low temperature activity. Question is, what is it doing to the chemistry to give you that low temperature activity and the low activation barrier? Well, here is the mechanism. Here is my gold particle. Here is my oxide support. And here is my vacancy, my oxygen vacancy in my oxide support. What we have is the CO, which binds to the gold. We have the water molecule, which binds to the oxygen vacancy and reoxidizes it. You then get hydrogen being split off and going onto the gold. You then get the hydroxyl reacting with the carbon monoxide. The hydrogen's combining, and you get hydrogen and you get CO2. So that is the mechanism by which this catalyst operates. And here is the activation profile. And what you find is that the largest activation step is this one here, and that is associated with the activation of water. The activation of water, you might think, well, that's dead easy, really, but actually it's not particularly easy. It takes a lot of energy. What we did was we had a look at what might happen if you charge the water, because of course, in a plasma, you're going to make ions. In fact, we know that you do ionize the water. If it's negatively charged water, it has a very high activation barrier for that particular step. However, if it's positively charged water, which you can see over here, the activation step is negative. In fact, you don't have any activation barrier. And so one of the things that could be happening here is you're ionizing the water. So therefore, you remove that as the rate determining step, the activation barrier goes down, and therefore you get high activity. Skip over this bit. Right, so that gives you an idea that we can do that. What else can you do with the plasmas, though? Well, one of the things you can do with the plasmas is you can use catalysts that you couldn't use under normal conditions. So metal organic frameworks, these are like zeolites, except the linkers are organic. And because they're organic, they are prone to oxidation, they're prone to thermal degradation, they're prone to reduction and prone to hydrolysis. So you can't really use them very well for many reactions in the gas phase because you require high temperature. But the plasmas allow us to do things at low temperature. And because you can do things at low temperature, you can now use metal organic frameworks. You can see here the activity of a metal organic framework in the plasma for the same reaction, the water gas shift reaction, gives you about 43% conversion. Under thermal activation, it's only giving you about 5% conversion. Importantly, though, the catalyst does not deactivate. It doesn't change its structure. It doesn't change its core volume. It doesn't change its surface area. You can see here before and after the plasma treatment, before and after the plasma treatment, before and after, and you don't get any changes. And so you are able to use the plasma activation to be able to activate MOFs in the gas phase. Right, I'm going to go on to, given I've talked too much, I'm going to go on to the last bit, which is biomass transformations. So this is a scheme that you can put together for how you might be able to use biomass in sustainability. You can take raw biomass and you can create hydrogen. You can get triglycerides and fatty acids from the raw biomass. You can make biodiesel from the raw biomass. You can use hydrogen and you can make alkanes and alcohol. You can make biodiesel, you can create glycerol, and you can make hydrogen. The key thing is these steps here both require hydrogen. This one here generates hydrogen. So you have a virtuous circle if you can get it to work. So the biomass over here, you can create the hydrogen that you need to then create the alkanes and the alcohols that you can then use for fine chemicals and fuel production. So can you do it? Well, one of the things we'd like to be able to do is take fatty acids, and you know that you can get fatty acids simply by extracting things out of plants. So can we make alkanes and alcohols out of those? Yes, you can. You can take stearic acid and you can reduce it to make sterile alcohol, heptadecane and hexadecane using a platinum rhenium on titania catalyst. And you might say to me, and you'd be quite right, because I haven't told you all the backstory, why is that interesting? The interesting thing is this bit here. You can do it at 20 bar pressure and 130 Celsius. If you do it with normal catalysts, this is 200 bar pressure and 250 Celsius, which is a lot more energy intensive. In fact, actually, you can do this at 5 bar and 60 Celsius. So you now have an opportunity to take a fatty acid that you can just get from biomass and convert it into basically what is a diesel substitute or a sustainable aviation fuel, or a long chain primary alcohol, which you can use as a surfactant. These are very expensive. These are slightly less expensive, but stearic acid is very, very cheap. You can control its selectivity as well. Here is platinum rhenium on titania. Gives you good conversion, very short amount of time, but gives you poor selectivity. The drop off here in making the alkanes. You don't stop at the alcohol. If you want to make the high value product, you reduce down the rate, you take away the rhenium, you reduce down the rate, and you keep the selectivity. You don't convert the alcohol into the alkane. So you can control that selectivity. Again, low temperature and low pressure. As I said, you can do it at 60 degrees Celsius. And you can see here the rate goes down, but the selectivity remains high. And you can do it at low pressure. This is 5 bar, 130 Celsius. Again, selectivity remains exactly the same, but the rate is a bit lower than at the higher pressure. So it's really the catalyst itself that is determining your selectivity. Whereas it's the conditions that determine the reactivity of the system. That's with stearic acid, but you can also do it with esters. So you can also get esters from plants. So the essential oils, for example, many of those are esters. They smell, but you can convert esters like this both into alkanes and alcohols. Again, you can switch the selectivity depending on whether you use the platinum on titania or the platinum rhenium on titania. You can see here, one's 98% selectivity with the platinum rhenium, and one is 99% selective for the alcohol when you use the platinum on its own. And I can go through that later if you wish me to. Of course, you've got to be able to produce hydrogen. And hydrogen production, not only the purification is important, you can obviously do it by steam reforming, but there are other ways of doing hydrogen production from raw biomass. And one of those ways is to use solar. So what you can do is you can take cellulose, for example, and make hydrogen via photocatalytic reforming of that hydrogen, of that biomass. A photocatalyst is something that uses the light to activate, for example, an electron. And so the electron goes from the valence band to the conduction band, and you use that electron to do reduction, and the hole that is left behind you use for oxidation. And it works. This is some photoreforming of glucose using titania, platinum on titania as the catalyst, and you can see here by shining light onto it, just having glucose in the in solution, you can see here you produce a reasonable amount of hydrogen. You can also do it with cellulose directly without having to use glucose, which is obviously a monomer. And you can see here, again, you produce hydrogen relatively easily. Most importantly, though, you can use raw biomass. In fact, this is literally some grass that I took from my garden. We put it in the reactor with the catalyst, we shone light on it, and we got hydrogen. So this means that you can produce hydrogen wherever you want. It could be in the mountains where there's no infrastructure. It could be in the town. It could be in your home. And you produce clean hydrogen. It doesn't have any CO there. It only has a bit of CO2 there. And that hydrogen that you produce, you can fit into a fuel cell, and that can then power your washing machine, your mobile phone, whatever it might be. It's at low pressure, therefore you don't have any explosion risks and so on. So it gives you an opportunity in Morocco, in the United Kingdom, wherever it might be, to be able to use the natural resources, as long as you're not using the biomass for other things. You don't want to use wheat to do this, okay? Because that's going to compete with food. You want to use something that's not going to be used for something else. And I think you have your... Yes, that's right. So you could use biomass waste or a weed or something like that. In fact, we've done this with sycamore. Sycamore is a weed at home, okay? So it just works perfectly well. One of the things that I saw yesterday, which is why I put this in, is a growth chamber that you have here. where you can change the conditions where you can grow things. And so what I thought I'd just show you briefly right at the very end was some willow. So willow is a tree that we grow in the UK. It is used for structural things, but actually it's not used a huge amount. But this is some willow that has been grown under different conditions. You can see some willow that has been grown over here. This is Rothschildiot willow that's been grown in the south of England, and then we've got some WB, which is Weatherby willow, which is grown up in the north of England. So the difference between the two is the north of England is wet, which is where Manchester is. It's wet and not sunny, and the south of England is drier and more sunny. Actually, what you want is the wet and not sunny weather, because here is the amount of hydrogen that you can get out of the same surface area of willow compared with the dry, sunny weather. So you can see here the conditions that you use to grow your plant can make a massive difference to the amount of hydrogen that you can produce, which is why I thought it was interesting, given you have a growth chamber. So I'd just like to say thank you very much for listening. It's a bit of a whistle-stop tour, but just some acknowledgements. In particular, on the CO2 front, you'll see someone's name over here, but in particular, Rebecca Taylor and Adam Greer did all the work, a lot of work on the CO2. The catalysis work is a whole bunch of people, as you can see. One of the things I would say is that we do everything via collaborations. So we do a lot in my group, but we collaborate with the people who have the expertise in what we need to do. So we have a lot of people. So Bill Graham, for example, taught us everything we needed to know about plasmas. Okay, in the photoreforming, Andrew Mills and Peter Robertson are world experts in this field. So we collaborated with them as well. But you can see here we have a large number of people. There are some common names. I think Sarah Ute's name actually fits in here, and there. So he's a very much a constant in my group, and I'd just like to say thank you to the funding agencies, in particular the Catalysis Hub, Supergen, and the EU, and our industrial sponsors and EPSRC. And thank you again for listening.
Thank you so much, Professor, for this very rich and inspiring presentation. I'd like to invite Jacques Jacquemin and since happy to join the panel here. I'm sure they have prepared some questions for you. Can I just ask a question about the activation in plasma?
The MOFs.
So what's the mechanism?
So the idea in the MOF case is that to be able to use them as a catalyst, you've got to have an active site, and the active site we feel in the MOFs is the metal. But the issue is, can you keep the metal linked in and keep the porous nature of the material, so you keep the surface area, for example, without destroying it? And of course, when you heat it, if you heat it to 300, 400 Celsius, then many of these MOFs will just collapse. You're using the plasma to activate the gas phase, so you can run it at low temperature. But that's not the whole story, actually. So you could think, well, that's a simple thing. But what's been interesting is that we've taken these MOFs and we put them under an oxygen plasma. We put them under a hydrogen plasma. We put them under a water plasma. We've combined some of these plasmas, obviously not the water, sorry, not the hydrogen and the oxygen, but the other ones together.
So what do you use as a sort of like microwave plasma?
So these aren't microwave. They're these are about 7 kV. They're DVD plasmas, so they're low temperature, 7 kV, about 20,000 hertz, low current. What we think, however, is these organic linkers disperse some of the charge, and so they absorb some of the plasma energy without getting destroyed. So you can activate the gas phase without destroying the MOF itself. So they are remarkably stable under the plasma tree. So
very interesting. Thank you.
Thank you, Professor, for this nice presentation. I have 3 questions related to the ionic liquid technology that you presented today. You probably believe in this technology, and my question to you is, what do you think are the advantages of this technology compared to other existing technology, and what are the limitations that you have encountered?
Okay, so the ionic liquids are liquid for the start, so they do have an opportunity to be pumped, and so there is an engineering advantage there. You can also tune them, as you've seen already, that they can be tuned for the absorption of one gas versus another gas, and so on. So they do have some advantages. They also have lots of disadvantages. Okay? So one of the major disadvantages is that they're expensive. You do have an awful lot of these that you can choose from, but do we understand everything about how they work? No. So there's a lot of complexity there. The expense means that you have to be able to recycle them at a very, very high efficiency. So losing 0.1%, 0.2% of the ionic liquid is costly. So you have to consider them as a capital expenditure rather than a consumable. Some of the ionic liquids, not the ones that I've shown here too much, but some of the ionic liquids, when they absorb CO2 or absorb other gases, get viscous. And so when they get viscous, of course, then pumping them becomes more difficult and so on. These ones here, actually, the viscosity hardly changes at all, which is a major advantage for use and reason why we actually chose to look at them. So there are advantages, but cost and complexity and the recyclability of those ionic liquids are the major disadvantages.
Okay, thank you. I will jump on this question. So you present the result on a dual mix with the 2 ionic liquids, the tails and the benzene, and with CO2 and SO2 gas stream.
Yeah.
And you show results that after 30 cycles, you reach 0.4 of mole of CO2 per mole of ionic liquids. How is this compared versus MEA technology?
So the MEA technology is good. It works very well. We are at 1. Yeah, it's very good.
But under the same condition?
Oh, I don't know about under the same conditions. Certainly with my understanding, but I would need to check, because SO2 does affect strongly MEA, as it would do here. So you'd need a guard bed of some description, but there are plenty of guard beds that you can use. But the advantage, the technology that we have here, is the guard bed, which is effectively the TET-based ionic liquid, allows you to get the SO2 out. Many of the guard beds that you have currently absorb the SO2 and don't release it. And SO2 is actually a very valuable commodity chemical. Making sulfuric acid is big business. So if you can capture that SO2 and reuse it, then that's an opportunity for you. It might change your economics as well.
No, not on ionic.
Okay, I will continue on this. So ionic liquids are not really produced at a large scale. I know that some companies develop their production, okay? And how do you see ionic liquid in 10 years technology? Because we start to speak about ionic liquid 3 decades, okay, approximately, and where we are in terms of the maturity of the technology. Because I know some companies start to develop process and so on.
So there are plenty of processes that use ionic liquids. Some of them use them as additives. Some of them use them as bulk materials. In the 80s, Eastman Chemicals had a bulk material that was making cyclic ethers that ran for 15 years or so, and that was an ionic liquid process. So they are not going to be the thing that saves sustainability of the chemical industry, right? So, but they can be one element of what we can do. You've got to choose your process correctly, though, and you've got to choose your the way that the ionic liquid is operated very carefully. It has to not only be an environmental argument, and there are issues with the environmental arguments because ionic liquids are perhaps toxic to some extent in the environment, but they're not volatile, which can be problematic in many ways. So if you can choose your ionic liquid so that it can be decomposed and remade, that's an opportunity to recycle them a bit more straightforwardly, potentially. You've got to look at the economic arguments as well, not just from the perspective of how much does it cost me to buy an ionic liquid, but how much does it cost me to recycle it? How much does it cost me both in terms of carbon as well? No? Because the manufacture of those ionic liquids is not straightforward either. But of course, as you move to a point where a particular ionic liquid, a given one, is then used in a large-scale production, the cost of it comes down. So there is a cycle here. You've got to gradually increase your scale, and as you increase your scale, your costs go down. But then you understand more about recyclability and so on. Where they're really well used are as additives. I've showed you an example of it where it could be used as an additive in the oil. They're used in batteries. They're used in solar cells. All of these things where they're used at small scale, perhaps in sealed systems, I think are probably where they're going to find most use.
You mentioned that transportation is responsible for carbon emissions. So do you think one day that we can capture CO2 from from cars' exhausts and use it simultaneously for fuel making via catalyst technology? And what do you think is the technology which is likely to make it for carbon capture? Do you think that ionic liquids, porous liquids, MOFs, or other material are likely to make it into this field?
The answer to your first question, I think, is no. So I don't see us being able to take the exhaust of a car with the amount of CO2 and the flow rates that you've got there, capture it and convert it on vehicle. I don't see how that works. I just don't. I don't see the flow rates and the efficiencies and the weight of the materials that we've got to do that CO2 capture. It's a very interesting point, but I don't feel that the weight of everything that we would have to use to be able to do that conversion would allow us to be effective in that scenario. If you consider, you'd have to have a trailer perhaps at the back of your car, which is then going to remove your fuel efficiency and so on. So I think that's unlikely. I think what we'd be better doing, in my view, the CO2, convert it into a liquid fuel, use it, so capture it from biogas, capture it from flue gas, capture it from the air, wherever we might want to do it from, take it into a fuel, put that into your car, and then put it back into the atmosphere and then convert it again. So I think that's a more efficient way of doing it, I think, and probably a more effective way. I'd like to think your idea would be great. It would give us a perpetual motion vehicle, but I can't see it really. I think that would be my view. In terms of whether MOFs or ionic liquids or porous liquids or any of these new materials that could be used for carbon capture are going to be used in the end, I think they all have a place. I think it might depend on the scale. I think it will depend very much on the ability to manufacture these materials and how effectively they can be used. But as I've shown you, I think it depends on what you're using them for. Not all ionic liquids are going to be okay to be used with a flue gas. Not all porous liquids are going to be able to use with a flue gas, but you might be able to use them for direct air capture. Do you want to do them on a distributed scale, or do you want to do them on a centralized scale? I think it depends on what you want to do, but they all can contribute to this. But I think it's very early days. I think we don't have, apart from the ones that have been commercialized, like the monoethanol. I mean, we don't have good materials that we can just do direct replacement on those yet. But we're getting there. It will take some time, and lots of people are working on it. Lots of very clever people are working on it, and but we will get there.
Just want to jump back on your what you think during the introduction about the calcium hydroxide reacting with CO2 to form calcium CO3, and there's many groups that they start to think to inject CO2 into the development of new concrete material.
Yeah.
So, what is your viewpoint regarding this?
Anything that we can do to remove the CO2 from concrete production has to be good. It's a massive production of CO, or producer of CO2 more generally. There's some work going on that have been looking at additives that can increase the strength of the concrete so that you can use less of it. So things like that will reduce down the CO2. If you can put CO2 into concrete and have it have the same strength and ability to do what you want it to do, then it has to be a good thing. I'm not aware of the results of that work.
And another point, you select the P6640 exam rate for the annual something oil, that's right?
Yes.
Why is exam rate?
It's a carboxylate.
Yeah.
And those carboxylates we find are good. The hexanoate is a good material to do NO capture.
Yeah.
It is also soluble in the oil. You've got to have something. It's an ionic material. It's an oil which is non-polar, so you've got to have something that's soluble in the oil as well. And the hexanoate allows you to have both solubility in the oil as well as relatively good NO capture as well.
Yeah, I have one question, which is carbon capture and utilization is a complex subject. It might involve biomass, catalysis, ionic liquids, and so on. So is multidisciplinarity important in such a subject? So I ask this question because in Morocco we have good scientists working on carbon capture. And do you think that we should combine our effort to do something in terms of carbon capture stuff?
I think you can see from my slide at the back here and this one here that I believe that collaboration and interdisciplinarity is critical for these. It's not easy to address these global challenges that we're talking about now just with a chemist in the lab. You can't do it that way. You need people who are experimentalists. You have to have people who can synthesize good materials. You have to have chemical engineers who can think about what the eventual process is. You've got to have people who can model those processes, both from a process optimization and process design perspective, as well as looking at the life cycle analysis from an environmental or an economic perspective. All of that has to come together for you to actually have an effective process overall. And so that interdisciplinarity is important. I think what I would say in terms of whether Morocco should do that, I think that depends on who you've got here and what their skill sets are. If you have all of the skill sets, then of course you can have a team that can do everything in Morocco. But the world is quite a small place, really, and we've shown that through the pandemic that Zoom and Teams means that you don't have to travel, you can do collaboration. It's better doing it face to face, as we've done here. It's much better to do it that way. It's much more effective. But you can do effective collaboration through the internet and have materials being posted and so on. So if you have a good collaborator elsewhere in the world that has a different material or a different source of that material that is effective, that you want to then test in Morocco for the types of CO2 emissions that you have out of the sources, then that's as effective as doing things internally. I'm not sure I would limit yourself to saying we must do everything in Morocco.
Yes, sure.
I think these things are much more global than that, I would say. And actually, as you can see, the collaborators that we have are across the world. I've collaborated with Joanne for years, and we've only been in the same country for a few of those years. So yeah. But I would say that Morocco has a real opportunity in this space. Now you have good natural resources, you have excellent people, really good skill sets, you have good industry, you have a government that wants to make a difference and so on. So you have everything going for you. So it like many countries, I think Morocco can really contribute to this space.
Thank you. I want to stay with the carbon capture. So you're using mass spectroscopy for quantifying the absorption ratio of the different gases. Could you tell us a little bit about how challenging that is in terms of exactness of the measurements that you are getting?
So mass spectrometry that we use, so we tend to use a small quadrupole mass spectrometer. So these are not terribly expensive, not compared with large accurate mass spectrometers, for example. So they're relatively cheap, they're relatively small footprint. The things that you have to watch with them is drift. If you're looking at quantification, you've got to think about the drift in the signal, not the drift in the actual mass necessarily, but the drift in the intensity of the signal. So that can drift over time. So in all of our cases, we have a tracer, and that tracer has a constant concentration, and so you can normalize your signals all the way through. You've got to be careful about making sure that the amount of gas that you're putting through the mass spectrometer is sufficient for the mass spectrometer to measure what you want it to measure, but not too high that causes a problem with it, and not too low that you can't see it. So there are technical issues and practical issues that you've got there. It's not completely straightforward, but it's certainly not difficult.
One of the reasons I'm asking is, especially if you're looking at many gases at the same time.
Oh, you're talking about masses. Okay.
Masses,
So,
knowing that they are ionizing differently.
Yeah.
Knowing that you have to ionize it.
So you do a lot of calibrations. So as I say, we have a tracer. So you will look at the signal. So you'll have a known concentration of gas that's going in. So NO in argon, for example, we then keep the argon signal constant. We do a set of calibrations with the NO. Your issues, you have mass overlap as well. So it's not straightforward, in particular when you have hydrocarbons there, to be able to do that, because hydrocarbons have many fragments, and so but the ratios between those fragments remain constant. So you can decouple all of the fragments eventually if you have enough.
So the pressure inside the mass spectrum doesn't allow any kind of chemical reactions to happen.
No, absolutely not. No. So that's all fine. One of the ways you can get away from some of these problems, but then you increase the expense, of course, and the complexity, is to use a time of flight mass spectrometer. And those allow you to have a much higher mass resolution than you have here. The advantage you have of a mass spectrometer over something like a gas chromatograph, which you could use for this, is your time resolution. So the mass spectrometer, you measure constantly, whereas obviously in the gas chromatograph, you take a sample, you wait 5 minutes, you analyze it, and then you take the next sample. And so you're having to interpolate the points and so on. So yeah, there are lots of advantages.
But if you're using time result measurements, you're also assuming that the composition is constant, sort of. You're not.
If you're using, sorry,
you're doing mass time result mass spectroscopy.
So if you do time of flight, then if that's what you're asking.
No, I was thinking that so to be able to
measure the kinetics.
To measure the kinetics, exactly, and to measure the changes that might happen to the composition, or the ratios, different ratios, in a temporal manner. So to actually understand how that changes in time, Is that possible to do?
Yes, absolutely. That's why we have a tracer there, because that keeps us with a normal.
Excellent, thank you.
I will follow the question, continue the question with the water gas reaction.
Okay.
We discussed quite a lot, and all this reaction, which is thermodynamic limited, but it's driven by kinetic, basically. And just to explain, it's enthalpy of reaction is negative. So when you increase the temperature, you decrease the equilibrium. So it's from thermodynamic perspective. So, and I would like to know the energy request for the plasma, really, if we want to move to larger scale. So this is not a limitation.
It is. So the DPD plasmas that we have are not efficient. You can measure the energy efficiency of those by looking at the amount of electrons effectively that you put in and the amount of products that you get out, and you find that they're not efficient. The reason why we use the DPD plasma is because on an experimental basis, they're easy. So you can do a proof of concept about what you want to try and do and whether or not this particular catalyst and try and understand what is happening using a DPD plasma, using our sinusoidal wave. However, we can move to something called a nanopulse power supply. One of the problems with the DPD, the way we do with the sinusoidal wave plasmas, is that, of course, as you've got a sinusoidal wave like this, quite a lot of the time, you're not at the peak voltages. No, in fact, you're mostly not at peak voltages. And so even though you're putting lots of energy in, your issue is that you're not at the optimal point. With a nanopulse power supply, you have a very sharp square wave where you're always more or less at the peak voltages. However, experimentally using those is quite tricky because you can buy nanopulse power supplies, but you have to insulate them very well. You have to put them in a Faraday cage because otherwise they are effectively an EMP generator. So these are electromagnetic pulses. So these could be used. So there is an idea, for example, in warfare that you create. You have an EMP that you put over a city. It cuts out all of the electronic systems completely. All communications go down, etc. If you can imagine turning one of these on in your lab and it's taking out all the computers and all of your other electronics, it doesn't. Your fellow lab mate will not be terribly happy with you, right? So practically, it is quite hard to do. So and you've got to be very careful. So we, from a lab-based experimental perspective, we use these sinusoidal ones. But if you then go to these nanopulse ones, then you have an opportunity to get much higher efficiencies. But your point is absolutely right. How good is that compared with thermal? Well, in theory, and it is a theory, every electron that you put in, you can generate your active molecule. Compared with putting a lot of thermal energy in, where you've just got a lot of vibrational states that you're not interested in potentially. So in theory, it should be much better. Practically,
probably want to add to the nanopulses the problem with overshoots. So they don't show in the actual signal,
Yeah.
because you would probably have some filter function that gets rid of them. But actually, in reality, they're affecting your plasma tremendously. So.
And there's a lot of work going on now, and you see lots of plots of energy efficiency and versus conversion and so on, of different types of plasmas, whether they be radio frequency, whether they be microwave, etc. And a lot of them have engineering advantages, a lot of them have efficiency advantages, and it's not absolutely clear which ones you should use when.
So we should also try to use high beams that we have here. And I think that could be very interesting.
Absolutely, I agree.
You can apply, I mean, you can choose more or less the energy region that you want to work with.
Yeah.
But if you want 20 electron volt particles or electrons in this case, you can actually generate.
You can tune in the activation of the molecules, and that is really the way to go eventually. I think, but we're not quite there yet, but it is the way to go. You're right.
And okay, so I continue with the catalyst. You're talking a lot about platinum. Platinum,
Indeed.
and platinum is very, very expensive.
Yes.
And of course, we did try. People try to use palladium instead.
Palladium is quite expensive too.
Yeah, that is expensive. The problem is, you think that this catalyst could be a sustainable solution for such a power?
So if you're talking to me from a purely catalysis point of view, and of course, if I look at the definition of a catalyst is something that accelerates the rate of reaction or allows you to have a reaction to happen without being used itself. Of course, it is completely recyclable.
Yeah. And
but then you have the
activation. So it's my next question.
So we've done a lot of work on how you reactivate catalysts. Can you redisperse catalysts, for example? Johnson Matthey did a lot of work on taking back in car exhaust catalysts and removing the precious metals and recycling that material and putting it back on the car exhaust catalyst. Sometimes the metal is perhaps the only metal that you can use. In our cases, that's not necessarily the case. Platinum is a very effective metal for many of the things that we do, but there are other metals that you could use. Have we examined those in detail? Not at the moment, but we've been more focused on what we can do with, so for example, in the photocatalytic work, what can we do with the biomass and so on to get the proof of principle, and then we move on to other materials. Carbon nitride is a pretty good photocatalyst in the visible light, for example. So we've done a little bit of work in that space, but there are a lot of opportunities.
Yeah, so my next question was more on the photocatalysis, but platinum titanium oxide. So explain people why you select platinum and titanium.
So
for this particular photocatalysis.
So those aqueous photocatalysts reforming the biomass using titania is well known. It's been used for glycerol. It's been used for glucose quite a lot, and so it was a method of starting from a position that we knew the photocatalyst. So we weren't so interested in developing a new photocatalyst. What we were interested in was, can we do something with biomass, and in particular, can we do something with raw biomass? What can we do with that material? So we started with a point where we could operate without by comparing our catalyst with the literature and so on for the materials that were being used then, and then moving it forward. We do need to go back though. As I said, we've used carbon nitride. That can be used. It's not actually very effective for what we're doing here. It can be used in the visible light. In actual fact, although we've used platinum on titania, what we have used is a particular type of titanium. So there are a number of types. These are generally mixed oxides between two phases of titania, the rutile and the anatase phase. The most ubiquitous, well-known, used material in photocatalysis is P25. So it's a particular material that used to be made by Degussa or Evonik. P90 is a slightly different form of that, and actually that is a much more effective photocatalyst for what we want to do with the P25. We would like to move into the visible range, but as I said, the carbon nitride stuff that we've used to date has not been as effective as we'd like it to be. We'd like to get away from platinum, but titania on its own is not good enough. But it's a nice sustainable. It's nice. It's relatively. It's low cost and so on. There are some issues with it potentially now, and so people are going to have to start to think about what else they could use. But for our work to start with, what we were interested in, as I said, was what can we do with raw biomass?
And we'll continue with the biomass, and you discuss about the generation of hydrogen and the use of hydrogen.
Yeah.
And could you just quantify, did you produce enough hydrogen to be used, or you still need a source of external hydrogen? Because it will depend on the efficiency of the reaction.
Depends on the rates.
Absolutely.
So again, it really depends on where you're using it and what you're using it for. The rates that we produce at the moment with our photocatalysis are nowhere near what you need. However, scaling up that process is not really potentially too much of an issue. So if the rates of one reactor is not great, you can scale up. There's not really a
The volume more or less.
So our volumes are small, so they're at 50 mils. So, but scaling out that with an array of solar collectors, for example, it would not be an issue. The amount of alkanes that we use in oil, you need an awful lot of lights to be able to convert that. So in the UK, I don't think we'd have enough lights to be able to do it. But in somewhere like Morocco, or Saudi Arabia,
Plasma.
so plasma could be used. So then again, it really is all of these contribute to what could be used, but they're not one single solution. So solar arrays to create electricity are one way to do things, but then you need very good battery technology. Now, if you want to do something that is using your vegetation, you could do steam reforming, but you need a heat source. You could use the electricity that you have from a solar panel generating that for a furnace, for example. You could generate plasma to do that. You could do the photocatalytic reforming of that to create hydrogen to go into a fuel cell to create the electricity directly. So it's not just one solution here. It will be a combination of solutions depending on what you want to do. But the answer to your question is no. We don't create enough hydrogen at the moment to be able to do that reduction.
And regarding regulation or UK regulation, what is the main strategy regarding carbon captures technology on decrease?
So it's wide. You've got everything from putting things down mines and doing enhanced oil recovery to capturing it from plants and doing biotransformations on it to make value-added chemicals. There's a wide variety of things that we're doing. A lot of this is being driven by legislation and economics. Tax is another one where people are sort of trading carbon tax credits. There's not one solution, but there's a variety of strategies.
If I jump back to the hydrogen what you produce, what is the main thought for you? To store hydrogen or to be used directly?
I don't. So from my perspective, I don't think that there are sufficiently good hydrogen storage capabilities at the moment. In particular, we have some very good hydrogen storage media, but then to try and get the hydrogen out again can be very difficult. Or you have, like the CO2 stuff, or you have things that don't capture it very strongly, but then you don't get large concentrations of it. But it's actually very easy to release. So in my view, I think that converting the hydrogen into a liquid or a solid fuel of some description or chemical. So, for example, you take benzene, you convert it into cyclohexane. You've increased its calorific value. You've now got a material that you can use as a fuel. Okay? Where you use that hydrogen to create something that we can use in our infrastructure at the moment. Hydrogenation of CO2, CO, whatever it might be, to methanol, methane. I think all of those are good ways forward because we can use our infrastructure. We do not have the infrastructure at the moment for hydrogen.
I want to give a chance to But maybe after your last question.
No, my last
Or
question
go
would
back
be,
to-
would be the last question. So,
Okay, very
so,
good. So do we have some questions?
Only one very simple question. Did you look at the life cycle analysis of CO2 capture technologies? I mean, yeah, because if we need to capture CO2, to convert CO2, we need catalysts, we need metals, especially novel metals. Novel metals are produced by mining industry. Mining industry is massive CO2 emitting. So in terms of life cycle analysis, is it positive?
People have, so we haven't done that in my group. People have done life cycle analysis of some technologies, and they are good in some cases, but they have lots of bad bits as well. So is the material that you're using toxic to the environment? It may not be doing anything in terms of the energy balances or the material balances, but then the environmental impact in a different way might be problematic for it. Or, as you say, the production of those materials could be quite a large issue. And in the end, it will generally come down to how you recycle materials, whether you can utilize those materials in another way. As I said, many of these industries are linked together. So, as I said, the fertilizer industry was linked to the amount of CO2 that we produce for dry ice, for example, in the UK. As soon as the fertilizer factory disappeared, we couldn't then transport fuel, which meant the government had to step in and provide funding for the fertilizer manufacturer to still be producing CO2, which we didn't want for the atmosphere, but we needed for other reasons. So it's a very, for me, it's a complicated ecosystem where we're just doing a life cycle analysis of that particular process doesn't tell the whole story. You've got to take that process with the coupled processes that you have elsewhere. And the way that our industry has been built up is that people have worked out what they can use byproducts for, and that creates another economy. Acrylonitrile is a good example. When people weren't using acrylonitrile, you couldn't buy acetonitrile anywhere because it's the byproduct. But we know we can use acetonitrile as a good solvent. As soon as acrylonitrile production went up, the acetonitrile price dropped again. Now, the reason why glycerol is such a low price is because of biodiesel production. But if we didn't have biodiesel production, glycerol prices would be much higher. So again, these are all interlinked, and that's the complexity. So taken on its own, yes, we can get a good life cycle analysis. Is it good overall? Well, I think that depends on other parts. So.
Well, I would like to thank you for the great and very interesting talk. My question is that if there is a way to use the ionic liquid, the one you produce, in direct ambient air technology, especially in the industrial zone where the CO2 concentration is very high, despite the relatively high toxicity of CO2.
So doing it with high concentrations of CO2 is not really a problem. We've done it with pure CO2, we've done it with 14%, etc. Ambient temperature for the capture is no problem. You need a slightly higher temperature. You can't do. We haven't found that we can do pressure swing absorption, so we can't just remove the CO2 and then you get all the CO2 back out again. You have to put some energy in to get the CO2 off the ionic liquid, and that's because it's a chemical capture.
So
it's not a. Yeah, you can't do it without some. You can't do it simple sparging. That doesn't seem to work. You need a little bit of temperature. It's not a lot, but you need a little bit. Yeah.
Despite the toxicity.
Yeah, I think so. Like I was saying about life cycle, you can the chemical industry is all based on taking energy from one point and giving it to another, coupling an exothermic and an endothermic process. If you can do that here, then you have an opportunity to do that. But you'll waste heat from one thing being used to take out the CO2 from another.
The scalability of the method of the plasma for hydrogen purification.
Yeah.
With catalyst.
Yeah.
Is there a way?
Yes. We've got to think about it in terms of scale out, not scale up. As you can imagine, the bigger the distance between your electrodes, the more energy that you need to put in. Okay, so if you have your electrodes very close together, you can have a very small amount of energy to create your discharge. If you have them like this far apart, of course, you need a lot more energy to do that. So you're limited to how far your electrodes can be apart from each other. People have done them at much larger scale, but if you want energy efficiency, in my view, you need them relatively close together. But of course, you don't have to have just one of them. You can have one tube and then another tube and then another tube, and so we have made them in a monolith, for example. So a monolith has got lots of channels, rather like in a car exhaust catalyst. So they have lots of channels right next door to each other, parallel, and then you create the plasma within those channels, which means you can have a high throughput of gas with the electrodes very close together. So it gives you an opportunity to do that. The other way to think about it potentially also is plasma jets. These are actually used in industry currently, where you can have the plasma vertical compared with the thing that you're trying to irradiate, and that then gives you a jet of plasma. In fact, I do in one of the very first slides I had on the plasma side, I actually had a plasma jet, but I didn't talk about it. Yes, so here, sorry, I'm just trying to analyze it. I say here is a plasma jet. So the plasma is being generated here, and the plasma is going onto a finger. See, and these things are used for medical treatments, in particular for skin treatments. They're very precise, but you could have an array of plasma jets onto a catalyst surface, and then create your and then do your water gas shift that way. So there are options of doing this scalability, but it's not simply about making something bigger. And so it's about doing things in a controlled manner.
Well, just more general question. So, what are your comments on coupling this CO2 capture with other techniques, like to convert CO2 to other things, like to energy storage or to plastic production?
So I think that is a very good way to go. There's a lot of work being done now, for example, in capturing CO2 and then convert it into polycarbonates, for example, or plastics that can be replacing virgin plastics like polyethylene or PVC or whatever. In fact, I was talking to this young lady who I can't remember her name earlier on about one of the things that we were interested in at one point was whether or not you could take the CO2 that you capture within the ionic liquid and have the ionic liquid in the plasma and doing the CO2 conversion within the plasma. Now, the problem there is, of course, the ionic liquid is conductive, so plasma is going to short out. But one possibility would be to take another CO2 capture media, like the porous liquids or the cellulose materials that I think you're looking at, and put those in the plasma. So you pass the flue gas over the system, you then you capture your CO2, you then pass the plasma over it with water, for example, or with hydrogen or whatever. You then either release the CO2 or you react the CO2 within the plasma, and then you convert it into the high value products, rather like we did with the electrochemistry. But it gives you perhaps a more scalable option to do something with. So I think it's a good way to go.
But what about the polymerized ionic liquid? Does that affect the efficiency of to polymerize the ionic liquids?
Okay, so
how does that affect the efficiency of that with this molecule?
okay, so people have put ionic liquids, so they've done a number of things. You can make polyionic liquids and you can make supported ionic liquids. They do affect this CO2 capture. We have put these super base ionic liquids on supports and they do decrease the efficiency of CO2 capture quite substantially. There have been other works where they have done the polyionic liquids and they've been relatively good. You have to do them in a fixed bed, of course, rather than in a bubble system. So you've got to be careful about making sure you've got good contact. But yes, they're an option.
Thank you.
Yes, I know we have a last question.
Yeah, so I don't know if someone is online. I don't know if someone online has a question. I have no idea.
I didn't manage to see if there are questions.
Yes, yeah, one question.
Could you? Yeah, okay. So we probably open Teams.
I don't need to. It's going to be.
James is here. So someone is asking regarding the CO2 RR. Normally, the ionic liquid acts as a catalyst, not a catalyst. What did you use as a catalyst for CO2 to HCOH?
Okay, so we didn't make acetic acid, we made formates. So the ionic liquid acts as a, so is it a catalyst or is it just a storage media? So our version is that it is a co-catalyst. You require an electrode surface and we use silver in our case. You can use platinum, you can use gold. Glassy carbon on its own doesn't work very well, but you need an electrocatalyst as well, and the electrocatalyst in that particular case to give the high efficiencies was silver. So silver plus the ionic liquid as the catalyst.
So, so regarding the hydrogen, so the hydrogen revolution, have you made a blind test without a sacrificial agent as issue may come also from the sacrificial agent?
Yes, so you can. So if the question is, did we do the blank? In other words, did we do water splitting? Yes, you get virtually no water splitting. So there is a very, very small amount, but it's very, very small. What are we doing when we're doing the reforming? You're effectively doing water splitting, but then taking out the oxygen by the hydrocarbon that you've got there, so you prevent the recombination of the hydrogen and the oxygen. That's one way to think about the process that we're doing. But actual water splitting itself without any other organic there is very, very tiny.
Last question. So
Before last.
can I say it?
Yes, of course.
They say that some group, Mazel group, I don't know, scientist, in 2011, that ionic liquid can bend the CO2 molecule through complexitation, which lowered the over potential. Does this has led to any CO2 to hydrocarbon or not?
I'm sorry, I apologize.
It's like you can
I can answer the question.
It's like a question.
That's a total conversation. Up the top. Up. We'll see the question probably.
Marvel's group in 2011 showed that ionic liquids can bend the CO2 through the condensation. Yes, we've shown that too. Shows the over potential. Does this has led to any CO2 to hydrocarbons as yet? Well, we can make formate, if that's a hydrocarbon. We can make formate. There's been very little. You can make oxalate, but as far as I'm aware, and I haven't read the literature recently, this was some time ago that we did this work. I'm not aware of anyone making higher hydrocarbons. So oxalate is a carbon-carbon bond being formed, but I haven't seen anything that's been making other materials. Partly, my understanding is that to make the carbon-carbon bond effectively, you need something that isn't platinum, gold, or silver. Something like copper is very good for it. But the copper dissolves in our ionic liquid. So it causes a bit of a problem. It dissolves the electrons.
Okay, last question. Oh, thank you very much. Oh, question here.
So the question here,
So you've spoken about the MOF, and as I know, ionic liquids are like a cation, whereas a large or smaller than the ion. That's why how you make ionic liquids are. They have a different size.
yes.
Okay, so why not we can like make a macro molecule about the mole, and that way we do an ion exchange at the same time with a smaller C minus or something like that. And at that moment, we can have an ionic liquid, which is stable without using plasma.
So I'm not quite sure I understand the question.
Okay, can we make an ion liquid with the MOF and which is stable without using plasma? Simply by making a macro one.
So you're saying instead of in the MOF, instead of having the hydrocarbon backbone, you replace the hydrocarbon backbone with an ionic liquid? Is that what you're asking?
No, I mean like if we can make an ion liquid based on the MOF. That, because you said we can make it by using the plasma, and we get a lower pressure and that's why I'm winning.
So the MOFs allow, so the plasma allows us to use MOFs in the gas phase. Okay. We can use ionic liquids in the gas phase, that's not a problem. And they don't decompose at lowish temperatures, but the ionic liquids themselves are still thermally unstable. So they will degrade, depending on which ionic liquids, but no, 200, 250, it depends on how long you leave them for, etc. But they will degrade at the high temperatures as well. We can combine potentially MOFs and ionic liquids together, but I'm not certain that that will give us any greater thermal stability. I guess my problem about using ionic liquids in the plasma is, of course, is that they're ionic and therefore they're conducting. So that's why I was interested in your porous liquids, about potentially we could, if they're not conducting, could we use those in the gas phase and do something with those if they weren't particularly volatile. So that was just a thought, really, rather than that. Well, it's an idea. But certainly creating MOFs that are more stable in the gas phase at high temperature, that would be ideal, because it would be good to be able to do thermal reactions using MOFs. If you made them more ionic, or coated them with an ionic liquid to prevent them from being oxidized, for example, that would be potentially very good. If you can stop the ionic liquid or stop the coating from degrading. So because your coating will still be exposed to the oxygen. So I think anything where we can make something that is more tunable, like a MOF is, that we can use in the gas phase at higher temperatures would be a good idea. I'm not sure whether that's answered your question at all.
No, I understand.
Okay, last question. Thank you. Well, first, thank you very much, Bob. Thank you very much to answer almost this question. My last question is, because it is your first time,
Indeed.
and at UM6P, we do hope that you will come back again. What would be your overall opinion and your main feedback to us? Because we want to do a lot of things regarding energy, and you talk a lot about CO2, hydrogen generation, different wave plasma, photocatalysis, and so on. So what would be your main advice, feedback?
I think it goes back to what I was saying to Hussein. I think play to your strengths. Really, you're doing some really nice work. You've got lots of natural resources. You have very good links with industry. You have a lot of excellent skills in the audience and within your student population and your postdocs and so on. You have excellent staff here. But you have, as we have in Manchester, as people have in Cambridge or Berkeley or wherever, you have a limited number of people. And so play to the things that you are good at, that you have good ideas, and then collaborate, would be my view. And collaborate with the best people that you can collaborate. I think then if you don't have the expertise in life cycle analysis, then it might be possible for you to buy them in. And you appoint another member of staff who brings that in, and that's one way to go. But you don't, to actually move on, you don't need to do that. You can say, okay, well, we need to have someone who does the life cycle analysis. We'll go and find somebody who can do that with us and collaborate. And that's how I think we will move on. And as I said, it doesn't matter whether they're in Morocco or Tangier or in Nigeria or in America or in the UK or in Germany. It doesn't matter where they are. You can collaborate, and I think you have a great opportunity to do that. And I think just in terms of your staffing, you're a new department. I think you just need to have a great, and from what I've heard, you have a really good strategy in terms of where you need to go. You've identified areas that you need to build and build critical mass in. Then as long as you have the right strategy, you will go far. And I think you have a great strategy. Thanks.
Thank you so much for your time, for being here, and we're looking forward, of course, to continuing our exchange and hopefully get some students involved as well.
I think that would be great. Actually, it's wonderful to collaborate across the cultures. I give a graduation speech each year, and one of the things that I talk about in my graduation speech is how great it is to interact with so many different nationalities, cultures, skills, etc., etc., and having those interactions is wonderful.
Great. Thank you so much.
Sorry, I didn't answer your question, I'm sure.
You did. Understood it. At the same time, I wanted to ask, do you know why the bad it's possible from we can recycle. You said you can't recycle. It's not bad.
The problem with some is a set of amino acid based their viscosity goes up by 10 times. Okay, and that's because the CO2. So one of the reasons why the viscosity is low with them before the CO2 is that because the binding site where the CO2 is prevents the molecules from being too close together, for example. So that the molecules can move past each other. As soon as you block that site, of course, the molecules they will sit together like down to a blanket, we would say, and so the viscosity goes up really very high. The advantage of the superbase ionic liquids is that doesn't happen. They go up a little bit, but they only go up by 2 or 3%. So it depends on the ionic liquid that you're choosing. If you choose a physically absorbing ionic liquid, so one that doesn't bind the CO2 very strongly, the viscosity hardly changes at all. But they don't bind a lot. They don't have a lot of CO2 in them. Yeah, I can't remember what Brennica's result was. It was about 0.04 or something, wasn't it? So it was only 4% CO2, mole percent CO2 for every mole of ionic liquid. So, but you can get the CO2 out very easily. So all of these things are a balance in energy, whether it be pumping, whether it be getting the CO2 out or CO2 absorption, the cost of the material that you've got there, whatever it might be. So that's why this life cycle question is very important, because it could be that you're much better off having a low capacity ionic liquid, so you can get the CO2 out very easily, compared with a high capacity ionic liquid that costs you a lot of energy to get there. No problem.
Such an amazing person.
Well, all skills like me.
Okay, so it's this. So,
I would say the questions part is, so questions were really fantastic.